name is Ekstrand. I would like to welcome you to my talk, A Little Windows with Your Mesa, for XDC 2024. A few months ago, on a desktop far, far away, it's my desktop, it's in my house, which is far away from Montreal, we had this. So most of you who work on Vulkan at all will recognize this as the Vulkan scene demo from Sasha Willems. This is one of the first demos that was released for Vulkan way back when the Vulkan 1.0 spec was released. But if you look closely, you'll see a couple of other things. First is this Windows taskbar running across the bottom. What's up with that? And also, wait, is that RADV? Yes, it is. This is RADV running on Windows 11. So let's talk a little bit about this. We're going to talk about why I did it, how I did it, and what this means for the future of Mesa. Now, about me a little bit. So my name, as I said, is Faith. I have been around Free Desktop since 2013, where I started off as a Wayland contributor. Then I worked at Intel from June 2014 through most of 2022. At Intel, I was part of the OpenGL Linux drivers team, where when I started, we're working on the i965 driver. I was part of one of the people who helped bring about No, the optimizing compiler stack that's in Mesa today. I also am the primary author and was the maintainer for many years of the Intel Vulkan driver in Mesa called Anvil. I was also the author of the SPIRV to No translator, partial author of the Intel Surface Layout library, and several other Intel-specific bits. While at Intel, I also served as a Kronos representative, where I participated in the Vulkan and SPIRV working groups on behalf of Intel and on behalf of Mesa as well. Since January of 2022, I am now at Collabora, where I work across the upstream open source Linux graphics stack, doing whatever is needed, wherever it's needed. Most of my effort the last few years has been focused around NVK and rebooting the Nouveau user space. However, I also work on other projects from time to time, and this is one of them. So let's talk about it. Before we can get into the details of RADV on Windows, we need to talk about graphics drivers on Windows, because most people here are used to working with DRM and not used to working on Windows, so it helps to lay down the framework. So WDDM stands for the Windows Driver Display Model, and WDDM2 is version 2 of that model. WDDM1 was introduced in Windows Vista, and one of the things it brought was much better separation between user space and kernel. So back in the Windows XP days, graphics was very much about sharing the screen and everybody doing front buffer rendering and rendering to the screen. And you can think about like the DRI1 model, only it had even worse separation between user space and kernel. So for instance, back in XP days, if you went to allocate a 2D image with 3 MEP levels and 4 array slices, you passed all of that data to the kernel figured out how much memory it would take, and handed you back the image with some layout information. The WDDM brings a much better separation between the two of them. It also brought about a composited desktop. Windows Vista was the first Windows version to actually do compositing. Prior to that, everything was good old-fashioned blitter. And when you drag a window across the screen, it would just blip from where it was to where it's going, and then redraw the bits where it was before and is no longer. This is very ancient X11, but this is the first Windows version that had compositing. It also brought GPU virtual memory support, so you could do actual process separation. And while WDDM1 does not require virtual memory, it does support it, and they built in the infrastructure. They brought in GPU work scheduling, so they could actually share the GPU more efficiently and have multiple graphical things going without potential issues of one thing hogging the GPU. And they also brought in GPU reset handling, which is another big thing for desktop stability. Back in the Windows XP days, if something hung, you just got a blue screen of death. Sorry, sucks to be you. You can still get that on Windows 10 or Windows 11, of course, but the core driver model now has support for resets, and most drivers these days have decent reset handling. WDDM2 was brought about in Windows 11, and that's what we're going to be focusing on today. WDDM2 brought explicit virtual memory management. So we had virtual memory before, but that was all being managed by Windows. It was all behind your back a little bit. And now there's explicit memory management, so you can start doing things like sparse resources. It also brought about a much improved synchronization model with context monitoring. So we have these things called monitored fences in Windows, which are basically timeline semaphores, only timeline semaphores plus. They're very nice. It's just a bit of memory that has a 64-bit value, and you can map it into user space, and you can map it into the GPU. It's pretty slick. So WDDM is an interface provided by Microsoft. So unlike the DRM interfaces, which is a bunch of ioctls that are completely ad hoc per driver, WDDM is an interface that is provided by Microsoft. And they have entry points for particular things. You can think of these as ioctls. So you can enumerate adapters, which are kind of physical devices. You can create devices in queues. You can allocate and map memory. You can do virtual address management, a la BKQ bind Sparks. They call it a paging queue, but it's the same concept. And they have work submission, where you submit work to queues. Then they have these synchronization primitives, which you can take the pointer that you get back and poke at that directly to see what value is in there. But they also have ways that you can wait on it, and you can tie it into the system and do things that are kind of like a event-FD type wait, where you can tie them into your event loop better than that. And they have some utilities for that. It also has the presentation engine. So they have a swap chain concept, which is not quite like Vulkan swap chain, but it's a similar idea. And that's all handled by WDDM as well. And all of this is standardized. Unlike the DRM drivers, where you have just a bunch of ioctls for whatever the heck the driver wants, WDDM2 is a standardized interface. Mostly. That's where things get interesting. So many of the entry points, there's about 6 or 8 of them, have a pprivate data field. And this is a pprivate data, which is a pointer, and then there's a private data size that goes along with it. That's the size of the memory being pointed to. And this memory is just passed verbatim between the kernel driver and the user space driver. It can contain whatever the IHV wants it to have, and Windows does not care. It just passes the data back and forth. And sometimes the pprivate data contains pretty important information. So, for instance, when you call create resource to allocate memory, the pprivate data actually has all of the information to allocate that memory. The only thing that the WDDM2 API really knows about is the fact that you're doing an allocation and that it's handing back a handle. All of the information about, like, if you have an image in there, what are the image properties, how much memory are you allocating, how is it cached, how is it mapped, what heaps does it go in, all of that is handled through the pprivate data, not through a standardized interface. When you go to create queues, there are these node and engine affinity things, but those also aren't really standardized. They're just there. And all the information about what kind of queue it is all private. Everything about command submission is also private. There is technically a field in the submit call that has an address to execute, but under the hood, it's all actually done in pprivate data. Nobody actually uses that one, at least not as directly as you might think. So, okay, that's good to know. How about API stability? Is this a stable API that drivers can really target? How does that work? And it's sort of stable. So all of Microsoft's APIs are stable. So the WDDM2 API is a stable API. There was a bit of a break between WDDM1 and WDDM2, where particularly around synchronization, they changed some things in a way that isn't really backwards compatible. But for the most part, the API just moves forward. But those pesky little pprivate data fields are still a problem. There is nothing stable about them at all. The hardware vendor is free to change them at will. And because, again, they're just data. Microsoft just passes the data from the user space driver to the kernel driver and back, and does not care what goes in that data. And so the hardware vendor's driver is free to change it. So how does this work? How does graphics not completely break on Windows all the time? And the answer is that the hardware vendor always ships the user space and the kernel mode together. And they're always updated together. When you update your graphics driver on Windows, even if it's updating it live, it is updating the kernel driver and the user space driver at the same time. And the only real requirement from the hardware vendor is that the kernel driver and the user space driver that they ship together work together and that they can share the p-private data. As long as those match, Microsoft does not care what goes in that field and does not care how stable it is. So, okay, is this API documented? That's always a good question. If we're going to try and write drivers against an API, is it documented? Well, yes, but again, sort of. So docs exist. You can find them at learn.microsoft.com. And most of the APIs in D3D KMTHK are documented. But they're not always good documentation. A lot of times it's just like, this is a thing that does this, and here are the fields. And not much else. And unlike a lot of other APIs from Microsoft, there's no examples. So like if you look at D3D12, the actual doc pages are often not great, but then Microsoft provides these fantastic samples that demonstrate how to do all sorts of things. And so you can go look at those as your documentation when the actual API documentation is maybe not the best. There's no examples. There's no like demo driver for here's how you write a graphics driver for Windows. That doesn't exist. Well, now it sort of does because I wrote one, but prior to me writing my RADV branch, there were no examples to go off of. I was poking blind. And then, of course, p-private data. Nothing in there is documented. Why would we document that? It's just structs in header files that are tucked away in the hardware vendor's Perforce repo. And unless you can get that hardware vendor to give you access to their Perforce repo with their Windows drivers in it, good luck. There's no documentation for any of it. So that's where we sit today. We have this API from Microsoft. It is standardized, which is good. But there's a lot of details that are left to the driver, and that's the stuff that we don't know anything about. So how do we get the drivers to cough up that information? Well, we build some tooling. So the first thing you need is you need a D3D12 driver. Now, I could have done this with the OpenGL driver, or the Vulkan driver, or D3D11, but I wanted the best thing to poke at WDDM2, and WDDM2 is designed for D3D12. So the best way to really be able to poke at WDDM and get back the information that I want is to do that through the D3D12 driver. That's going to be the best match, or at least that's what I was figuring. Also, the D3D12 driver is available inside the WSL2 container since 2020. And this is really useful, and it makes a lot of things easier, at least from my perspective as a Linux developer. So you need D3D12 driver. We also need some carefully targeted tests, and I have a link there to my GitLab, where you have my wddm2-pdd-re repo, and it has a handful of targeted tests that invoke D3D12 and then scrape the p-private data out of it. Oh, and we need a way to scrape the p-private data. So for that, I have a branch of libdxg, and we'll talk about that a little bit more in a minute, that allows me to get at those p-private data. And with all of those pieces in place, we poke at D3D12 and we see what comes out. So this is what poking at D3D12 looks like. This is my create queue test. So what this is doing is it's creating 3 different command queues, a direct queue, a compute queue, and a copy queue. And the direct queue is basically a universal queue in Vulkan. So what it does is it iterates over my list of queue types, and then it calls create command queue for each queue type. In the middle of this loop, you will see something called pddlog2file. This is a little C++ class that the moment you create it, starts logging all p-private data that come out of the driver from that point until that class is destroyed. And this allows me to be very, very targeted about what I log. So I can create a scope, create a pddlog2file, and then invoke a single D3D12 call, and then end the scope, and that guarantees that what I get logged is exactly what was invoked as part of that call. The PDD loggers are also nestable, so I can have multiple of them going. I can have one that logs everything, and then I can have one that just logs each VK create, or each create command queue. And it's really quite a flexible mechanism. And And what this does is just prints out to a file every single WDDM2 call that gets made and all of the p-private data is in those calls. And then I can try to relate the information in my test, maybe that's the size of the memory object I'm trying to allocate, to those p-private data, and then try to use that to figure out what goes inside of them. Beyond that, it's a lot of the same reverse engineering techniques that a lot of us are already used to, where you poke at the driver, you try different things, you see what changes those make in the commands, or in this case, p-private data, and you use that information to try and figure out what everything actually means. So what do I know? I've done a bunch of reverse engineering effort, but how close am I to knowing how things actually work? So with the adapter info, which is the way that you get most of your device information, I know very, very little. I know where they put the PCI ID in the adapter info, but basically I don't know anything else. And the reason for that is because unlike basically every other p-private data, the driver private adapter info isn't something that I can change. I can't change what command I throw at it and see what info it gives me back. That doesn't work. It's just one big giant blob. All I can do is look at what the driver, how the Windows driver initializes it and do the same thing and then call and see what it fills in. But it's really pretty limited what I can do because the only way to change what's in the adapter info is to physically change what card you have plugged into your machine. If we want to reverse engineer this, it's going to be tricky, if I'm honest. It's going to require a lot of hardware, and it's going to require a lot of just running it on every GPU we can find. That's unfortunate, but we also do have the PCI IDs, so that gives us more than nothing. We can also get the things like the amount of memory through standardized interfaces, so those aren't, so at least we have that information. But that one is going to be a challenge. When it comes to memory allocation, I would say I know about 20% of it. I know enough to allocate a memory object. I know where the client requested size goes in the field. I know what the align size goes. I roughly know how to control memory placement, whether it's in VRAM or system RAM. I know kind of how to control mapping. But there's a lot I don't know. The size is duplicated about 10 times in the struct. I have no idea why. Shared images work somehow. Like all of the image data about what kind of image it is goes into that p-private data, and I don't know what that looks like. It could be that it's just some adderlib struct, but I'm not sure. Again, it's enough to allocate raw memory objects, and then we can, lay them out however we want. But if we start trying to share images with D3D12, then we're going to need to know more details. I also don't really know how mapping works. Like, I have it working, and I think it's placing things where I think they should go, but it's a lot of, if I see this combination of things in RADV, then I plummet to this arbitrary combination of things, and I don't actually know what the individual bits do. There's some more reverse engineering work that needs to happen to figure that out. For queue creation, again, 20% maybe. I know enough to create a queue. There is a p-private data, but as far as I can tell, it just has the size of the p-private data struct at the beginning and nothing else. I mentioned node ordinal and engine affinities earlier, and they map to something, but we don't really know what either one of them means in the case of RADV. And the mapping is not something that's standardized. So presumably we get that mapping from the adapter info somehow, but I don't know how. What I know right now is that for my card, 0-1 gives me a graphics queue and 2-1 gives me a compute queue. But there's a lot of details we don't know yet. For queue submission, on AMD, I would say I know about 80% of what's required to submit to a logical queue. There are hardware queues, and I have no idea how those work. The D3D12 driver does not use them by default right now on AMD, and so I'm just using the virtualized queues. But I know basically how that submission works. I know how prelude and postlude command buffers work. I know how hardware contexts, or I don't really know how hardware contexts work, but I've got a decent idea. But enough to get stuff running. So, like, overall, it's a lot of stuff. I have some demos running, I can pass some CTS tests. But I'm also clearly not doing it correctly, because if you try to run the full CTS, your box will power off inside of 5 minutes. Because even though AMD's drivers are way better at hang recovery than they used to be, they ain't perfect yet. And that's pretty easy to demonstrate. So again, it's all very work in progress. It's making progress, but I haven't put a whole lot of effort into it. And just so you don't all get super disheartened that this is all I know, I literally have put like a month into this project. I put a couple of weeks into it back when I first joined Collabora in 2022, and then I put another week and a half into it this year. So I haven't put a lot of effort into it, and I've been able to get to the point where we're rendering something on screen. So that's not nothing. So I mentioned earlier that I did all of my reverse engineering with Windows Subsystem for Linux. And we should talk a little bit about why I did that. So before we do that, let's talk about WSL and what graphics looks like there. So Microsoft added graphics to WSL in 2020. And the way that this works is that they para-virtualize the WDDM2 interface and expose the interface into the Linux guest. So there's a DXG kernel driver that maps the WDDM2 interface in the host to ioctls in the guest. And then libdxg in the guest maps those ioctls back into the WDDM2 interface. And the WDDM2 interface that is provided to drivers on Linux is basically exactly the same interface as the one on Windows. The only difference is that the size of wchar is different. And so there's a little bit of translation for that. And there's a couple of other APIs that don't make sense. But for the most part, it's the same interface. In particular, it's exactly the same pprivate datas. And this means that the driver teams at the different hardware vendors have to make sure that those pprivate datas, like the structs, build the same on Windows and Linux with the same binary interface. Which isn't too onerous because it's just C, but it does mean they have to be a little bit careful with it. And then at the hardware vendor, they provide a Linux build of their D3D12 driver. And it's the same D3D12 driver that they run on Windows. It's just been built for Linux. And then all the other APIs inside the container, like OpenGL, Vulkan, OpenCL, all of those are layered on top of D3D12. And most of those layered drivers are Mesa drivers. There's the dozen drivers, a Vulkan driver on top of D3D12. We've got GL on 12. And then the OpenCL driver is half Mesa driver. It uses the Mesa compiler stack, but the actual OpenCL ICD is in a different project. There are a couple of counterexamples to this, like they made an exception for CUDA so that you can get CUDA inside the container. But for the most part, they expose D3D12, and that's the going plan. But they expose all of WDDM2, and that's what I'm taking advantage of. So why did I use WSL? First of all, again, it provides exactly the same interface. So what I'm doing is the same as what I would do to develop the driver on Windows. I'm not calling into different entry points to do it on Linux. It's the same interface. But it lets me use a Linux build of Mesa. And that means I didn't have to sort out all the Windows build issues. I didn't have to figure out how to get Mesa to build. I didn't have to figure out all the dependencies and put them in directories and figure out all my paths and figure out how to get Meson to work. I could just build Linux Mesa and run it. It's still using WDDM2. It's still using the Windows kernel driver, but it's a Linux build of Mesa. This also means that I can just sync builds between my laptop and my Windows. And so my developer flow for working on RADV on WSL is exactly the same as any other driver I'm working on. I have a test machine. I type code on my laptop. I build it on my laptop. I rsync the binary to the test machine. It's just that the test machine happens to be running Windows. And I have Fedora, same version of Fedora in my WSL container as I have on my laptop. So I can just rsync stuff and everything works. Very, very nice developer flow if you are a Linux developer. It also means that I can use LD preload to replace libdxg. And there are ways of wrapping and hooking DLLs on Windows. I could have hooked the relevant GDI32 DLL on Windows, but I don't know how to do that. And I didn't want to spend a bunch of time learning about Windows trickery around DLLs to try and figure out how to stick myself in between the signed graphics driver and the signed GDI32 DLL. That just sounded like a mess. But inside of WSL2, again, I can just use the tricks that I already know and love, and we can get the information. The other thing is that WSL exposes a Wayland compositor to the guest, and that means I didn't have to figure out Windows system integration for Windows. I could literally just use the same Wayland Vulkan WSI that we've been using for the last 8 or 9 years and use it in WSL. So basically, I'm using it because it let me cut a lot of steps out of my development process. Long term, obviously, if we want to ship Mesa on Windows, we're going to have to sort all these things out and build it for real and real Windows system. But this allowed me to focus on what I was interested in, which was WDDM2 and the reverse engineering work. And with all of that, here it is. This is RADV running inside of WSL2 on top of AMD's Windows kernel driver with displaying over Wayland. If you're looking at the frame rate there, and you're thinking that 75 FPS is a little bit low for an RX 780 or 7800, yes, it is. And the reason for that is because, unfortunately, the Wayland that they're providing inside the container uses WLSHM, and there's like 4 or 5 CPU copies of my frame buffer happening every frame. And that's why it's only 75 FPS. It's not because the card isn't able to run at speed. It's literally just because the Windows system path is kind of rubbish right now. Okay, now for the question you've all been waiting for. Why did I do this? First of all, why not? We're Mesa developers, we're open source software developers. A lot of what we do is, frankly, for the heck of it. And that's a good thing. That's a positive thing. It means that we're experimenting and we're learning and we're growing and the code bases we work on are growing with us. So why shouldn't I do an experiment like this? But also, there are reasons. So I've been talking to various people for many, many years about Mesa on Windows. I've had many conversations internally inside Intel. I've talked to people at other hardware companies. And why shouldn't we be using Mesa? Like, the Mesa drivers are really good. Why are people writing their own OpenGL drivers these days? Why should Windows drivers continue to be closed source? There is no good reason. Every time I talk to a hardware vendor, they always have reasons. Like, oh, there's all of this IP inside of our Windows driver. Oh, we're using all of these NDA interfaces from Microsoft. We can't make that stuff public. They've never actually asked Microsoft if they can make it public. They're just assuming. And it's all complete nonsense. And so part of what I wanted to do is just prove them all wrong and show, yes, you can write an open source driver and have it run on Windows. Also, for RADV in particular, frankly, it's better than AMD's Vulkan driver. And so why shouldn't they use it? Why shouldn't that be the driver that Windows users get? It's already tested on all sorts of games. It's fast. Acco is better compiler. Why shouldn't they be using it? And then also, like, part of what I do and have done for a long time is talk to game developers. And I'm in a bunch of Slack channels and other things where we're talking. And they hate closed source drivers. They are tired of getting seg faults deep inside of NVIDIA's driver stack and not having a clue why it's there. And some drivers ship some hardware vendors ship debug symbols, but even there, you get a stack trace, but you can't actually look at the code. All you have is a stack trace. And basically, these issues are undebuggable unless you have the ear of somebody at the hardware vendor. And if you're a big game company like EA and you're working on the next Battlefield game, then yes, you have access to people at NVIDIA. But if you're some little indie dev, no, you got nothing. So developers who work on open source drivers or who are able to develop against them absolutely love the experience. And they love being able to talk to the developers directly via the issue tracker and maybe even implement their own features. So there's a lot to be gained from open source drivers, and I want to be able to see that brought to Windows. And going a little bit big brain here for a second and putting on my technologist hat, think about for a minute the world of compilers. Once upon a time, everybody wrote their own C compiler. Microsoft had a C compiler, Sun, HP, SGI, they all had C compilers, Intel had ICC. C was the standard and everybody had compilers, kind of like OpenGL is the standard and everybody has drivers. There were also some weirdly specific compilers, like when I was at the supercomputing conference in Austin, Texas in 2006, there were people running around trying to show all sorts of weird, bizarre specific compilers. Like here's a compiler for this particular generation of AMD Opteron CPUs that we've optimized to use those instructions. And today, there's 3 compilers. There's LLVM, Clang, GCC, and MSVC. That's basically it. Like, there are still compiler teams that exist. Intel still has ICC technically. But basically, all of these teams are just taking LLVM and like optimizing this one use case they really care about. There's really only 3 compilers. And why shouldn't Mesa be the GCC of graphics? Like, NVIDIA always writes their own, is always going to write their own Vulkan drivers because they're NVIDIA. But what about everybody else? Why is ARM going off and building an entire OpenGL software stack? Why is Imagination going off and building an entire OpenGL software stack? There's no point. We already have the infrastructure in Mesa. We've proven that the drivers are good, and that the issues are because we don't have armies of developers, not because Mesa isn't any good. So why shouldn't Mesa just become the GCC of graphics? And if that's going to be the case, we need to support Windows. Yes, this is a bit of a plan to take over the world. You all know my secret now. But seriously, I do think we are very close to getting to the point where people need to stop being in the business of writing full driver stacks, and they should be writing backends. And I really do think that Mesa is the thing that we have the potential as an industry to crystallize around, and I want to see that happen. So, last question is, can we actually ship this mess? I talked a little bit about backwards compatibility and the problems there, and the answer is probably, but not if AMD interferes. So we can probably ship it without them helping us, but if they decide to just change the interfaces around on a whim, we're kind of sunk, and there's nothing we can do about that because there's no stability guarantees. If we got their help, if they actually, dropped us a few struct definitions, it would make things go much, much faster. But there's kind of a weird situation there where, yes, we can do it with reverse engineering, but unlike the hardware, the interfaces can potentially change out from under us. But the good news is that the p-private data structs, even though they're not stable, they're not stable. Like, hardware vendors don't change them on a whim. Even for internal development, you want to be able to update your user space driver without upgrading your kernel driver all the time. Like, unless you're actively working on a user space kernel feature, you want to be able to just rebuild the Vulkan driver and run it on whatever kernel you happen to have installed. And so it's pretty common when you're working inside of a hardware company to be able to run on a 6-month-old or even older kernel driver without any issues. With my own branch, I said I started working on it 2.5 years ago, and then I revved it 6 months ago. And when I did that, I didn't actually have to change anything in order to get the stuff that was working 2.5 years ago to work again. Like, just not that much has changed. So it's a lot more stable than you'd think. And what the people, like the Turnip team, has been shipping on top of the Qualcomm kernel driver for Android for a while. And that's proven to be more stable than you'd expect as well. So it's not crazy. In an ideal world, the hardware vendor would provide something like libamdppd.dll, which gets uploaded along with the kernel mode driver and gives us sort of a stable API that wraps those things. That would be the kind of ideal solution. And I've thought about, like, I've got some prototypes for what that would look like. But another option is that the hardware vendor could just ship Mesa. Like, upstream Mesa could just track the latest kernel driver and hope there's not too much churn, and then whenever they cut a release, they ship Mesa alongside the D3D12 driver and alongside the kernel mode driver, and they verify that the combination works, and it'll be fine. The downside of this option is that bisects get to be a bit of a problem, but honestly, bisecting this is no worse than trying to bisect the Windows drivers today, and it's why they try to let some slippage keep working. Overall, there is some work to be done to figure all of this out and to figure out what it would actually look like, but it is possible. This isn't a crazy thing that couldn't ever be done. It's just some processes would need to be figured out. So what's the impact of this on Mesa? We'll need some runtime support. There's already a merge request that adds WDDM2 support to the runtime. We will need to be able to build on Windows, but we already do that for Dozen, GLON12, and LavaPipe. We'll have to improve the Win32 WSI code. But again, like, there's code that exists. We just need to make it more appropriate for hardware drivers. and then we'll have to do some debug. And the good news is that most of the titles are already running on Linux via DXVK, and like there's way more titles that are running on Linux via DXVK than native Vulkan titles on Windows. So most of the debugging is still going to happen on Linux. And it might mean we get some new developers. There's a lot of developers out there that are Windows devs that would love to poke at their driver stack, but they're Windows developers, and poking at it on Linux is daunting to them. As much as we like Linux, they don't. And if we suddenly start supporting Windows, we're going to get some new developers, and that will be something we have to deal with. But honestly, new developers is a good thing. So is this actually a good idea? Well, I'll leave that up for you to think about. Thank you for coming to my talk, and I hope to see you all next year. Bye.
Hey, I guess, I mean, just to sort of put the question back to you, I mean, you work with AMD developers all the time in Mesa. I mean, have you asked if we could give you the struct definitions? I mean, I could certainly talk to the Windows team. I mean, I was going to say, just to sort of turn the question around on you. I mean, you work with a number of AMD people every day in Mesa. Like, have you asked anyone about talking to the Windows team to get the structures for you?
I have talked to some people, and I think that there are people who are amenable to it. But most of the people who work on Mesa are pretty isolated from the Windows teams, or at least that work on the user space side. I don't know how much the kernel people talk, but I do have contacts, and I have been asking those questions. But I haven't gotten far enough along where there's a need for that. So it's likely that's a conversation we're going to be having. And like I said, there are people who are amenable to it. So I think there is a decent chance we'll get AMD's help, but I'm not going to make promises on their behalf. I mean, if you want to start that conversation, go ahead and send me an email. Sure. And we'll have a chat.
Thanks.
Hi, Faith. Great presentation. You mentioned that a lot of the performance drop was because you're copying on the CPU 5 times. Now that surprises me. 5 times? I can maybe guess 2 times. You have to read back from the hardware, and then you have to upload that back to the hardware after it makes the jump through WLSHM. Can you explain more about the 5 that you need?
Okay, so I'll go through the ones that I know about. So first, we don't have any sort of user pointer support in the Windows kernel driver that I was able to find. It might exist, but I haven't found it. And so that means that we are doing a copy from the frame buffer that we rendered on into a host visible buffer. And then because we don't have user pointer, we have to then mem copy that into the WLSHM object that we allocate. And then that gets shipped to the compositor. The compositor then has to copy it across the VM boundary. And then that gets eventually copied another time, probably as part of the upload process to actually get it onto the GPU to display it. There may be another copy or 2 in there somewhere that I haven't enumerated. I think that there are discussions, and Microsoft has talked about trying to come up with a 0 copy path or a much, much, much fewer copy path, but that's the annoying situation that we're in today. I think eventually what would be good is if they could actually be sharing, basically doing something like VirtIO is doing, where you can actually share GPU objects across the VM boundary, but I don't know how much work that would have to take them to get working. And we can certainly tighten things up on the inside the container if we can do some sort of a user pointer thing, so we can do our download blit from the GPU directly into the WLSHM object. That's what you get if you use WLSHM on Linux today. That's what you get in most drivers, is that we user pointer the shared memory buffer, and then we split directly into it, and that gets rid of one of the copies. But again, it's very hacky because I was focused on getting something working, not getting something working optimally. And it's very much shortest path to pixels on the screen.
Thanks.
How hard would it be for you Windows working, talking to what is basically a Linux KMD? And by that, I mean VirtIO GPU with native contexts with a VirtIO GPU kernel driver in Windows.
I mean, that's basically what they're doing inside the WSL2 container. They're not emulating the DRM driver. They are paravirtualizing the WDDM2 interfaces. It's not terribly different from what VirtIO is already doing today on Linux. It's just Microsoft's variation on that. So it's not running like the GPU isn't separated off. It's still running on top of the Windows kernel driver. It's just over a similar-ish interface. But the way Microsoft did it is a little bit cleaner because there is literally no difference between the interfaces, and it's the same sort of ioctl forwarding concept under the hood.
Okay, that makes sense. The reason I ask is that someday I'd like to support GPU acceleration in Windows VMs under CubesOS, and since context, that means running Mesa's backend. That means using Mesa's native context support under Windows, and I'm wondering if that could be
Okay,
work.
that's an entirely different question that I was thinking you were asking. I don't know. So if we can get access to that paravirtualized DRM driver, then rendering stuff on top of it is pretty practical. The problem is that I don't think the rest of Windows is going to work on a graphics driver that isn't WDDM2. WDDM2 is pretty fundamental to Windows's entire graphics stack, and so trying to swap out for an interface that isn't that is likely not going to happen, at which point the question you're really asking is, can we write a WDDM2 kernel driver that talks to DRM under the hood? And I have absolutely no idea what that looks like.
Gotcha. Because there is one, but there is a VirtIO GPU WDDM2 driver out there, but it's not for native context, and it's still experimental.
Yeah, and there are multiple people who have done some sort of WDDM2 driver that basically talks GL inside the host. Like VMware has theirs. There's the VirtIO one. I don't know what else, but that's a very, very different thing than trying to get Mesa running on top of an existing WDDM2 driver. And I do not know what the kernel side interfaces look like at all.
Okay. The other question is, you said that the Windows box crashed.
Yes.
Have you reported any of those given that it's a kernel crash and user space should not be able to crash the kernel, have you reported any of those to AMD's bug bounty?
I have not. I also haven't put a lot of effort into figuring out why it crashed. Like, if I know what to do to bring it down, then reporting that to AMD would absolutely be a thing. But this is more of I got the demo working, and I'm like, what's the worst that happens if I try to run the CTS? And then I go back 5 minutes later and my box is dead. And apparently that's the worst that happens if you try to run the CTS.
Okay.
I think I was also doing a multi-threaded run, so that probably hammered the kernel even worse.
That doesn't even work on Linux on a bad day. For figuring out the physical device info returned from DXG, like, have you considered, instead of having to possibly test every card under the sun, tried like just returning crap from the DXG call and then seeing how the UMD responds to it? Like, I bet we can get something about from the registers it then tries to set in the command buffers.
That's actually a really good idea. I had not thought of doing that, but that is a very interesting way of going about it. But before we can do that, we need to know what the forward direction of the API looks like in more detail. Like, if something impacts engine affinities, for instance, we need to know what the forward direction looks like so we know what to expect when it changes. But that is definitely an interesting approach to trying to reverse it. What I'm really hoping is that we can just get somebody at AMD to email me the struct. Like, that's the ideal solution.
Doesn't hurt.
Hey, so you mentioned you built this under WSL, and I'm kind of curious if your sort of vision for Windows developers not necessarily dealing with these funny APIs, that they need NDAs and so forth for, were to come to pass. Do you imagine that there would be folks on Steam needing to publish games and asking their users to install WSL in order to get a driver, or do you think there'd be a more elegant way of doing that?
I just did WSL because it made the reverse engineering hackery easier.
Yeah.
But in terms of what we could actually ship, I mean, it's using exactly the same calls. Like the interface provided by libdxg and the interface provided by gdi32.dll are literally just different by wchar size. So it's a matter of getting Mesa to build on Windows, which I think RADV is building on Windows already for reasons. It's just a matter of sorting out the build system issues and sorting out the Windows system layer, and then it should be able to just run as a Windows Vulkan driver and talk to the Windows Vulkan loader. We might need to do some stuff on the loader side because that is a little bit different on Windows, but but those entry points already exist in Mesa for Dozen. We just need to make sure everything's hooked up correctly.
Okay. And do you think this would be doable with like other LLVM components? Like RADV is just one utility, obviously, that like interprets NIR and does like a compile path to GPU code. I'm curious, do you think like maybe some other utilities might be doable in a similar way?
Possibly. I'm not sure exactly what you're thinking there. I have considered porting other drivers. I got started on NVK, but I didn't actually. I got distracted by writing kernel abstractions and didn't actually get it ported. But it certainly would be possible to build a branch of the Intel driver or a branch of get NVK working. Like, it's all possible. It's just a matter of where the time gets spent and how the reverse engineering work goes, and whether or not we can get hardware companies to throw us a bone.
There are some utilities that are, I think, used in NVCC, which is NVIDIA's compiler stack, that might be interesting for this. But yeah, I'll leave it there. Thanks.
You've asserted that you can't replace the kernel side, and so you have to, obviously this whole project is about reverse engineering the interfaces to the kernel half of the driver. I mean, it seems quite obvious that, given the reasons you've laid out for replacing the user mode driver on Windows, that replacing the kernel mode driver would offer the same benefits. I understand, of course. It would require, administrator privileges to install that half. But you also said that it would be impossible because Windows relies on a WDDM model, and I'm curious, like, in what way that is true.
It wouldn't be impossible to write an open source kernel driver. The kernel side of the WDDM2 interfaces are a little harder to find. I don't know how much of that stuff is public. I don't know that Microsoft is against making it public, but there just hasn't been need. So we certainly could do that. The thing we can't do is not use WDDM.
Why is that?
So, because WDDM is baked into the core of Windows and everything graphics on Windows.
And what relies on WDDM?
The compositor, the Windows desktop itself. Microsoft's components are all DX12.
Can you well DX12? I mean, it has a user mode driver. I mean, can you replace like just the parts of use the parts of WDDM that are relied on, like which is probably adapter enumeration and composition, but then like the entire graphics pipeline, you could just go through private interfaces for that?
I don't know how much of that is possible. With hardware contexts, you can short circuit some of it, because that's designed for submitting direct to firmware. But WDDM2 is very much the glue between the kernel and the user space. And I don't know that you really can get around that without doing some pretty funky stuff. And I think if you tried, it wouldn't integrate with the rest of Windows well. Like if you actually want a desktop, you're going to have to provide a DX driver and a WDDM2 based kernel driver.
Sure.
Yeah,
My impression from looking at this area is that, I mean, yes, it is a glue, but it's also a very thin glue that's basically just meant to cross the user kernel boundary. And since, there are private data structs, you need the user mode driver to be calling into those. So the user mode driver could just be doing whatever else it wants to get into the kernel path.
And you can tuck anything you want to into the pre-private data. So as long as it fits roughly into the object model, you can do anything you want. I think I commented in my presentation that the submit has an address in the submit, but nobody actually uses it.
Yeah.
Like,
right.
it was intended for, this is the beginning of your batch buffer, but in reality, everybody just shoves a pile of stuff into pre-private data, and that's their submit process. So there is already a lot of customization that happens under the hood.
This is probably something that the React OS project could help, I guess. Have you talked to them?
No, I haven't. This isn't something that I've thrown a massive amount of time at, so I haven't been off talking to a bunch of projects trying to get help with it. It's been let's see how much of this I can get working. It is possible that the React people would know some details that would be helpful, but again, most of the difficulty isn't with the Windows interfaces. It's not with figuring out how those interfaces work. It's with either go write your own kernel driver, which is not something I really want to do, or figuring out how to run on top of AMD's kernel driver or NVIDIA's kernel driver. And that's a completely different thing that the React project might know something about, but
what I meant is that they're probably interested into getting their own drivers. So maybe they start writing drivers if we poke them.
Yeah, that's possible. I haven't talked to them about it at all. I haven't talked to very many people at all. Hopefully the React people will notice it on the XDC agenda or something.